So we are back with our friend, the machine tool. You have seen this structure a lot of time. What we're going to do today, we're going to use this, structure to compare the use of shell elements and beam elements. We have done it, yes. We will do it again, yes. We will see different things, of course, otherwise you just see the record last week. Because we have done many of the things we already had, well, we would have done today, I have uploaded the CA2, CAE, and journal files to the WeDid folder. You have to, you know what to do, you have to open the Explora resource from the virtual desktop, and then copy, paste it on the Y drive, so that basically we can open it in Abacus. Me, I did it already, so I'm just going to directly open Abacus. Okay, I'm going to wait for you to copy paste it on Y and to open the machine tool shell, which, as you can imagine, is the one related to shell. It's going to say, but it's from a previous release of Abacus. Should I translate it into the new one? Of course, otherwise it will not work. And then I'll just wait a bit for everyone to be on board. While you open it, this is also a good exercise because it will be common that, of course, if you keep working with finite elements, it will be common that you open files created by others. In general, it's more complete simulations. Here it's kind of in between, but let's say, I don't know, you are a replacement in a company for a person who had an accident and suddenly had to leave the company for a couple of months. So now you have to take on their files, and let's see how to take a simulation file that was interrupted while creation, and let's see how to check it. How to check it is very easy. No, what we have to do is just to follow the usual path and see what the other person did. First of all, this is the This is more or less the shell element, the shell model we're going to study, except we don't have the holes and also the these thickened, let's say, reinforcements. But it's just a shell element, shell element model that represents the steel structure of the machine tool. We're going to do something similar to what we did last time when we did the beam elements, which I don't have here, however. That is, encaster the two columns at the bottom, and then apply a load in the center of the cross section. Let's open the Abacus file. Here, as always in the tree, we have some of the things that were done and some of the things that were left not done. As you see in the parts and also in the assembly, No, it's only in the parts, but sometimes also in the assembly. You have the parts that are kind of locked, which means that we cannot really do anything. This is done in general to prevent any modification to the design. It's up to you. If you want to keep it locked in general because you know that the geometries are fixed and you know you don't want to mess it up, it's okay. But for us, we're going to need to. If you want to unlock them, you can just select both and then right-click and unlock. Are you okay for me to unlock the part? Yes. And now basically we can do stuff on these parts. We're not going to at the moment, but still it's useful to know. As always, you know that here we have the two parts. We have one column and one crosshead, of course. You have seen that this sort of, you see the yellow planes, the datum planes. These were used to create these partitions. You kind of understand why. Last time we used partitions to have a proper mesh, but actually here, why? It's because below here we're going to put the columns, and here we need a reference face to actually apply the load. So, okay, this is more or less nothing special, I would say. We go to property. This is green, which means that a property is already assigned. Let's check if the person who did this did it properly. If I go to the manager, I see that steel was created, and let's check which steel is the classic 206,000 megapascal. The section, yes, this person was correct. They applied a shell homogeneous type of section to a shell elements correctly. The thickness here is 8 millimeters. That's fine. And we have 5 integration points through the thickness. Now you know what that means. This is for the crosshead. Actually, final check. Let's also check the section assignment. Yes, only one section assigned to only one part. Okay, so this is fine. Let's check if the column, this is the crosshead. Let's check if the column was also assigned the same property. It looks like it because, of course, we don't have any other section. So probably, yes, this was the same section assigned to the column as well. Okay, property is fine. Let's go to the assembly. Here we see that our colleague did not only imported the crosshead, but not the 2 supporting columns. So this is for us to do. Always double check that you actually have one instance. You remember that when you put one instance, you have that thing to flag or deflag, that it can easily overlap 2 instances in the same place, 2 identical instances in the same place. So you won't be able to say, to distinguish if you have 1 to 500 instances all in the same place. Here we have 1 because actually I see it here on the tree. How do we proceed? Actually, this was interesting because you can actually check how to import multiple instances. This you know how to do, but maybe also orient them and rotate them one with respect to each other. So, as always, create instance. As always, this is one of the most dangerous menus in whole Abaqus. So the first thing I'm going to do is auto offset. So anything that I create is clearly visible. I start with column, and then I click apply. And then I insert another column. Don't do it. Look what I mean. If I deflag this, it's going to put, okay, here is going to put it here behind the crosshead. But if I put another column, it's going to be in the same location. So I'm not going to be able to see if there are 1 or 2. Anyway, let's keep this always on. And now either apply and cancel or okay, only one of the 2. Click OK, and I have it. Now, actually, let's do both. The intelligent thing to do now is this. As you can imagine, we're going to take the columns, rotate them, put the crosshead on top. But if we just do this in the assembly, there's not really a contact or any interaction between them. We're going to create a tie constraint. Tie is sort of perfect bonding constraint between the square, one of the square of the column, and the corresponding surface on the crosshead. Because we're going to do this, of course it's good to define already now what we're going to assign. Why? Because now we can see both. When they're going to be one on top of each other, we're not going to be able to select one of them individually. We are, actually I'm going to do it and show you how it works. But the smart thing would be, let's just do it now so that later we will be much faster. To do this, what is possible to use is these sets. So if you go in the assembly tools, set, create, and here I can select geometry, node, or elements. In this case, we can select geometry only. And let's do this. Actually, wait, better like this. Yes. And now I'm going to call this crosshead, maybe CH is better, crosshead positive Z. Why? Because I want to give meaningful names for later. I'm going to call it crosshead to identify clearly what I am defining. Positive Z is, I know that I'm going to create just this set, these geometrical sets. So positive Z of the crosshead means the square that is in the positive direction of Z. I don't want to use left and right, and it's pretty clear why, because where is it? Here, now it's left, and now it's right. If I look it from the other side, left and right, of course, now are switched. So if I call this left, maybe I use a bad view, and in the end, I get confused. Again, always think that someone else is going to open your file like we're doing now. And if you call left and right, then you don't know what is left. So for me, this is going to be positive Z and negative Z. Continue. Let me go back. Okay, let me zoom in a bit. Continue. Geometry, continue. Select geometry for this set. I want to select 1. It's going to be difficult. 2, 3, 4, 5, and 6. Remember to hold Shift instead of Control, and done. And now we have created the set, and you can see it here. CH position Z in the tree. Let's go back in the other view. We have to create the correspondent on the column. Because we have 2 columns, look what happened. The part is called column, but it was important in the instance as column 1 and column 2, which for us is completely meaningless. So I'm going to do column 1, right click, rename, and this is going to be now and forever pos Z. So positive Z. So this will be the column that will end up on the left in this view. And this means that this will be the column negative Z. Which means that now I can go to, which means I wait a bit. I hear a lot of clicks, so I'm going to wait a couple of seconds and then I start again. Okay, of course, like I said, the next step is tools, set. No, I didn't say okay Google, I just said okay, sorry. Okay, tools, set, create. And you can imagine this is going to be, for example, positive column. See, yeah, I'm going to column. That's it, honestly. Positive column. Square. Yeah, positive column. Continue. Select the geometry for the set 1, 2, 3, and 4. And this is done. Now, in principle, we do it also for the other column, of course. But again, I want to show you also the command for when you don't do it and then you remember, oh, I had to do it. So we see both commands. So for now, we're going to leave it like this. And then what we have to do for these two columns is rotate them and then bring them below the corresponding. So this is the command to rotate, of course, rotate instance. Select the instance to rotate. Let's start, for example, from this one. Done. Select an axis or a start point for the rotation vector. I'm going to select first this point, for example, and then this other point. And this will be the axis that defines the axis of rotation. Now I want to go 90 degrees like this. Is it plus or minus 90 degrees? In principle, I have to do the right-hand rule and try and set. I can also just say, okay, let's try 90. Is it the one I want? No. Okay, then go back with the black arrow, and then I just put minus 90. Yes, this is what I want. Okay, I do the same for the other column, of course. Done. Once again, this is the rotation. Actually, I can just select the axis. Yes, 90 degrees. What happened? Wait, because I think I selected both columns. So of course, remember, be careful to select only one column, because otherwise it's going to rotate everything. Again, select an axis is still this axis. Sorry, I clicked translate. Rotate this around this axis. 90 degrees, yes, okay. Okay, you should have, more or less everyone should have something like this. To translate the columns, we use this command. Let's double check that, yes. So this is the positive Z, so this will go here. So with this command, translate instance, select instance to translate the column that I called positive Z, done. And then here, Abacus is very convenient actually, because I can select 2 points as a translation vector. So of course I can select, for example, this point, yes, and bring it there. So from here to here. Position of instance, this one, yes, definitely okay. And this is done. Of course, I do just the same for this one. Done. From this point to this point. Okay. Done. And here we have it. Everyone more or less has something like this. All good? Okay. From assembly, we go to the step. In the tree, I actually see that there are 2 steps. So one step was already created. So let's just do step manager, edit the step 1, and let's see what happens. Not what happens, what the other person did. NLGeom off. Was this intentional, or the other person just didn't know that this command existed? We will never know. Does this go on or off? Again, at the moment we don't know. Let's launch a simulation and see. Let's start with off. If we get that for I don't know, 400 millimeters, no, like a 1 meter beam, it goes down by 5 meters, maybe it's large displacement. Incrementation, of course, if you didn't know that command, for sure it doesn't know this command. So anyway, we can leave it like this and see what happens. One thing that is always important to double check is also the field output, because I told you, sometimes one of the worst things is you launch the simulation, everything is good, simulation works, you get the good results, but you don't save the file, the result, and in the end you don't have what you need. Let's have a look. Here we have contacts, we're not interested, but okay. Strains, it's fine. Stress, displacement, reaction forces. This all looks okay. Nothing to check?
The points to the section.
Yes. We're using shell elements. Output as shell, beam and layered section points. Let's leave it as use defaults and let's see what happens. But indeed, this we have to change. Okay, dismiss. So I save, step, interactions. Okay, first of all, let's do the thing you already know more or less how to do. We want to apply a load at the center of the cross section. How to do it, you know, reference point, coupling, and then we apply the force on the reference point. By the way, that load is meant to represent this, the spindle, which honestly I don't know what it is, but basically it's, I don't know, it serves what this machine does. Anyway, and it is 500 newtons. So we have to apply that load. In principle, we have to select the reference point. If I do tools reference point, however, yeah, I don't see the reference point that I want in the middle. Actually, yes, I select it there, but are we sure it's the correct one? Honestly, I wouldn't take that risk. How can we actually see the point we need to select? For this, we're going to use the command that is here. And if you don't have it, it's in View Toolbars, View Cut. You have to put this on, because otherwise you don't see those two commands. If you do it, you have to click both. First, this one, and this is pretty useless because you cannot change anything. With the manager, you can start playing a bit. How do we use this? The idea is that basically it provides a cutting plane perpendicular to X, Y, or Z, you decide. For us, it's useful to have, for example, a Y normal to the cutting plane. And then with this slider, I can look for where I have to go. So what I want to do is go all the way up, so the whole thing is not cut at all, and then slide it very slowly until we just remove the roof, let's say. Because now I can see inside the crosshead. And if I do tools, reference point, here it is. If I don't trust it yet, I can still rotate it better. Yes, that's exactly the point I need. This is the point I want. RP1. Once this is done, of course, I click again here to deactivate it because I don't need it. I'm done with the reference point. And now the reference point, the good thing of the reference point is that even if it's hidden by something, I still see it. Okay. Yes, the coupling. So you know how to do it. Create constraint. Coupling, you know coupling. You know I like to call this with the reference point name that I use. For example, this I'm going to call RP1. I go into this view, the frontal view, let's say, yes, this is useful. I'm going to tell you something now because once I received a very worried call about this, but you know why? I mean, in principle, you're looking in front of the machine tool, but you also have these commands to turn perspective on and off. If you turn the perspective off like this, then you're actually on the front like you were drawing on paper, and you actually see all the things straight. With the perspective on, you see the size. It's not that this is not in plane, of course. Okay, coupling RP1. Yes, now coupling RP1. Okay, continue. In this thing, by the way, I select RP1. By the way, you see here, when we select stuff on the thing, here I have create set. This is the abacus doing what we did before, just because he prefers to use it. It doesn't change anything for us. Me, I just turn it off because I use the input file and I like it clean, and this makes other line in the input file. Okay. So select constraint control points, RP1, done. Constraint region type. Now we're going to do this. Node region. In principle, I want to select all the lines that are here. All of the lines. How do I do it? I do this. I click and drag to select all of this. But then I'm left with all this stuff I don't want. So with Control and click and drag, I remove it again. Remove, remove, remove also RP1. Honestly, I never understood if that makes an impact, but let's just remove it just to be safe. And we're left with this. And if I rotate around, you see, I have selected exactly what I need. X and down. Here, I touch nothing. I don't need any particular setting of the coupling. Click OK, and that's it. If I look inside the crosshead, I should see exactly the spider of the coupling. Okay, let's go back to our view. Actually, this is better maybe. And now we have to create that constraint I was telling you before. It's a tie constraint. It's another constraint that is very used, is very common to use because it's a perfect bonding between two entities. This is again here. Create constraint. Tie. Once again, let's give meaningful names. Let's start with the one we created in a smart way. So this is positive Z. Look what I told you before. Positive Z now is on the right. When we started, it was on the left. But now at least I know what positive Z, which one of the columns is. It's the one with the positive. Continue. Choose the main type. Now we want for the main to be the crosshead, the secondary to be the columns. Let's go with, for example, surface. Now look at this. Select regions for the main surface. Again, here I should select these lines of the crosshead, but I have no idea which one are these. Actually, sorry, not go back with the arrow. Not surfaces, but not the region. Yes. Again, in principle, I should select this, but I have no idea if these lines that I'm selecting is of the column or of the crosshead. But because we use sets, I can go with sets here. And again, I want the main to be the crosshead. So crosshead, positive Z. I can also be extra safe and highlight the section. Yes, that becomes red. And this is fine. Continue. Secondary type, again, a node region. And again, positive column. And now, because I have highlighted the selection in viewport, that becomes purple. So I know that the two are overlapping. They're correct. I didn't mess it up. Okay, I'm happy. I click OK. And here I have tied everything. Let's say I forgot to do it. Should I go back in the assembly, delete everything, rotate again? But of course not. How do we do it? Very easily. Let's go back here. Create constraint. This is the negative Z. Is again a tie. Continue. Choose the main type, node region. Okay. In general, if you have used sets before, sometimes you start already with a set. If you don't want this, let's just click here, selecting viewport, and you go back. Probably you already have it because I have it already. So now I want to select those rectangles, the contour of the square below the crosshead. How do I do it? I use these commands here. I open this, create display group, and then I go to part model instances, and here I select the crosshead, and I click replace. Alternatively, I can select the column and click remove. It's the same thing. For example, let's do this. I select column negative Z and I remove it. Remove it, you see it, it removes it. Add it, it adds it. Replace it, it adds it and hide anything else. But anyway, now it's hidden. It's still there, huh? In the tree, it's still there. The feature still exists. I'm just not seeing it. That's the whole thing. So let's maybe rotate it a bit just to have a better view. Okay, and now I can select points. What? No. Node region, yes. And then I can select exactly 1, 2, 3, 4, 5, and 6. Done. Now, select the secondary type. Once again, node region. Let's go back to our frontal view. And let's open again the create display group. Now here again, with column negative Z, I can do replace, for example. If I do replace, I'm left with only the column. Be careful to remember what is up and what is down and not to select the wrong edges. And now I can select these edges. Once I have selected the upper square, I click done. The menu is still the same as before. I just click OK. To bring everything back, it's this full circle, full orange circle I have here. Replace all brings everything back. Notice that also reference points, datum planes, coordinate system, they all disappear. Interaction we did, we have tied the columns to the crosshead. We have created the coupling and the reference to the reference point that we're going to use to apply the load. Let's move to the load module. Here I have nothing, I think. Yes, indeed. So we have to create everything, basically. Okay, so here, create boundary condition. We're going to apply, actually, this is a, it's kind of hinges, I would say. And you know I like to use displacement and rotation, not the encasser. I click continue. And look, we're creating it in the initial step. Is it okay? Is it initial or step 1? It depends on what we're going to do. For here, maybe, no. For here, it's better to use it in the initial step, because then we're going to modify a bit the step. So let's create it in initial so it stays forever. Displacement and rotation, continue. Select the regions for the boundary conditions. I want all the bases of the columns. Sorry, I'm not asking questions. Do you want me to repeat? It's fine. You want me to repeat some stuff? Am I going too fast? Or? Okay. Okay, so we go here. No, we go, I don't remember everything. Yeah, this one. This is the front view again. And here actually is useful to use the perspective off. Because if I turn perspective off, then I can do this and be sure that I'm selecting all the edges that are there. Once again, with Control and drag and drop and drag and click and drag, do this, and I'm left with only the bottom parts. Okay, I click done. All displacements are prevented. Now here you have to be extra careful because these are shell elements. So they have a rotational degree of freedom. So if I constrain the rotations, I'm going to actually do something to the model. And I'm going to get a different result than what I had before. Here we want it free. Okay. Save. Create load. In the initial, of course, there is no load that can be applied. I call this force, for example. So we go to step 1. Concentrated force, continue. Reference point 1, I can select it very easily. Done. We want to apply 500 Newton as a weight, so going down, which means that this is minus 500 as the CF2. And I click OK. Actually do, yes, if I want, there is also this tiny command that activates a sort of transparency, and I can see that the arrow actually is pointing. What did I do? Save. Okay, sorry, I saved. Yes. Save. Mesh, of course, yes. We have to mesh the parts. No, it's meshed. Nice. So we thank the other person, and then we just right-click on job. We create a job and we launch it. So job, this could be, for example, 01 static. Nothing static, machine tool, I don't know. Okay. Right click, no. Right click, we submit the job. And now we wait. Okay, it's completed. Let's go to the results. Let's see what happens. For example, if I plot contours on the form shape, I'm going to check the Pomies stress. These are all plates of 8 mm of steel. Is that realistic? What is happening? You know what is happening. If I go here, common options, I see that I have 316,100 value as deformation scale factor. What does it mean? That all the displacements are taken by Abaqus and multiplied by that number. Why? Because it allows us to see what is actually happening. To see the true deformation, I have to do uniform here and put 1. as a deformation scale factor. If I click apply, now you can clearly see that this is the undeformed shape, and now this, look at the board because I'm going to do it, this is the undeformed shape. Basically it's invisible. This is why this, yes, it's an exaggerated version of it, but at least we know that it's exaggerated. Why? Because let's have a look at the displacement. 0.00139. So 1 point some microns. I mean, that's small displacements. For sure. Okay, so this is it for the deformed shape. We are happy with this. Makes sense. Let's have a look at the stress. Yes. Let's have a look at the stress. Here we get the von Mises stress, and I see everything that's happening. I even see here possible stress concentrations due to the fact that the column and the crosshead are interacting. Now, let's say I want to see, again, these are shell elements, I want shell elements that are mostly, especially the crosshead, they are mostly bent. So I would expect a sort of a linear trend in the thickness of the stress. Let's have a look. If I double click on XY data, ODP field output, continue. Let's have a look, for example, at the stress 1,1 for an element that is anywhere here, close to the center of the beam, not exactly there maybe, but at least close to it, somewhere here. I click this, I click done, save as is, dismiss. Okay, this is what we have. It's linear, so it's correct, no? It's what we expected. Is it linear? Yes. This is not a finite element graph. This graph in finite element, it's a line. It's not a plot, a graph. We go here. We plot the markers, show symbol. I don't know why Abacus makes it so small, so let's also ask for the large ones. Okay, now I can see them. See them? Yeah. Okay. It's not linear because it's linear. It's linear because I only have 2 points. And it's different. Why I have 2 points? Because of what we said before. Yes, I have 5 integration points in the thickness, but I didn't ask to plot the result, to plot and to save the results for all of them. To do it, I go back to step. Here in the field output manager, here edit, and here output at shell, beam, and layer section, specify, and I want the output at 1, at 2, at 3, at 4, and at 5. From 1 to 5 with commas in between. Now I click OK. And I relaunch the simulation. Submit, and OK. Again, what has changed from before to this simulation is not the solution. Abacus did all the calculations and computed the same stresses that we're going to have now. The only difference is it didn't save it. It did compute, it did use all the 5 section points. It's not doing additional calculations now. It had computed all the stress in the 5 points, but in the end, it just saves the first and the last. Why this? Because, okay, here you don't see it, but then if you have to save everything, then it becomes, the output file becomes very large. Anyway, again, exactly the same results. I do the same thing as before. Double click on XY data. I made a mistake. This is the command I should have used. Thickness, not the ODP field output. But you would have got the same. In the thickness, a line between 2 points. Trust me, it's, you can try it later, but trust me, that's correct. Anyway, thickness, continue. S11, if I select any other element, I mean, potentially the same, but it's difficult. So let's just select one, save, SE, okay. Thickness, and now I can once again here show the symbols. Look, now it's linear because it's linear. I mean, it was also before. The thing is that now I have the proof. Now I know. Before I was guessing. Clear? Question? Doubts? Okay, this is our results that we got with the shell elements. Let's try and open the file. Open the other, not with the, sorry, yes, the other file, machine tool without the shell. Okay, once again it will ask save, yes. Once again it will ask for updating the new version. Okay. Here, for reasons of timing of the lesson, you just have to trust me that everything is correct and just launch the cubic job. So right click and submit. Okay, completed. Results. The deformed shape more or less is similar. If I have U 0.0015, before I had 0.0139. It's okay. You see it now that this was faster, this is easier, it's easier to look, it's easier to model and everything. It's faster. We are, okay, no, that's shell elements, but still, we are modeling beams, actual beams with beam elements. So I honestly, if I have to bet, I wouldn't bet too much, but I would bet that the solution of the beam elements is more correct. But I have no information on stress concentrations, local values of stresses, maybe because of contacts one against each other. This, of course, I lose everything. So, which one is best? Again, it depends on what you want to do. If you just need the displacement in the middle, does it really make sense to do all the effort of doing that whole? Again, okay, here we did it in 1 hour, so it's easy, yes. But again, scale this to an actual job, to an actual thing that lasts months. So this is mostly what I would say. Beam elements, because they implement the theory for beams, in general, they tend to be very accurate and very efficient. But you have limited output of what you can analyze. Let's do now, clear question now? Let's do that, let's do now another thing. We have this, whatever, this spindle, and we want to analyze the dynamic response of the machine tool with a mass concentrated on the crosshead. And the mass, of course, is the spin. You have to think that the crosshead is like here. So this is the crosshead. And from here is something like this. It's not to scale, huh? Something like this, basically. So it's even eccentric, no? It's not, we put it in the reference point that is in the middle, but actually it's not there, really. Of course, from a static, okay, this is an interesting question. That was a preliminary analysis. We put the reference, the load on the center of the beam, and we got some results. Actually, it's not on the center of the beam. It's on the side, which increases all the stresses, all the deformations. It makes everything a bit more complex and stuff. So what we did before actually can be considered as a sort of preliminary analysis. This said, we had stresses in the order of 0. megapascals. The displacement was in the order of 1 micron. How bad can it get if instead of in the center, we put it just a bit on the side? I'm not saying don't do the analysis. I'm just saying we can do it a bit more relaxed. It's not going to be hugely catastrophic if the assumption that we had of putting the load in the center is not going to be catastrophic, of course. But of course, for the dynamic analysis, this will be a lot different if you have a concentrated mass in the center or somewhere else. Okay, so let's do this. We have to go back and open again the machine tool shell, the one we were using before, so with all the changes made. So basically in the assembly, we have already everything prepared. A wise thing to do now would be copy the model that we have here. This is going to be model 2 dynamic, for example. Be extra careful now that in the tree, you close model 1, you open model 2. Here, you have model 2 selected. And as a proof, you have model 2 underlined in the tree. Because if not, you're going to work in the other model and you're going to be make messes. Okay, so the first thing we're going to do is step. In the step manager, I don't want anymore anything that is related to the first dynamic, the static analysis. So I just unflag this. Sorry, I put a cross. Basically, I click here and it gets crossed. Then I create a new step, create. And this is the same that we used for the other example, that was the frequency step. Continue. We want 5 eigenvalues, which means the first 5 modes of vibration. And click OK. This here I'm fine. Let me double check that the field output for the 2 is okay. Yes, we just get U, of course. Step is done. Assembly is done. Interaction Now, you see that the ties stays, and this it's okay. I don't need anymore the constraint RP1. So I go into the tree and I deleted it. Okay, to delete, yes. And then in the assembly, I also delete the reference point. Assembly, extend this. Features, RP1, it's here. I'm going to wait to delete it because if then you ask me where is it, I'm not going to able to show you. I just click on it and cancel it. Okay, to select, yes. Okay. This is done. Now, what we have to do is, do we really need to model all this mess for a dynamic analysis? What is the, so mechanically it doesn't do anything, it just adds weight. We trust the supplier of where we buy this thing from the company that it works, even if we don't trust that we pay them, so it's their responsibility anyway. For the dynamic analysis that we're doing, what is the only thing that we're interested in? The mass. The mass and where the mass is located. Sorry. And where the mass is located. So we receive this, we created it, we receive it from a supplier, whatever. We import it in a CAD model, CAD software, any CAD software, I think Abacus does it, and we get the mass properties of this thing. It weighs 306 kilograms. These are the moments of inertia and so on and so on. Okay, this is good. This is the center of mass. It is located here on this view and here on this other view. So we have to create a point that is there. For example, you know that there is the command of create a point from as offset from another point. So for example, let's say we want to use this point. We need the horizontal distance, and let's say 185, and the vertical distance that is going to be 450 divided 2 minus 65. Let's do it. We do tools, datum, point, offset from point. This is the point we said we want to use, but again, now it's just as an example, you can use anyone. Of course, because we're using this point, we have to be consistent. So x is in that direction. And I forgot. 185. So 185, comma. Then it is 450 divided 2, 225. Minus 65, 160. But, yes, 160 up. So, 105, comma, 160 or 60? 60. 60, comma, 0, because along Z is 0. So, 185, comma, 160, comma, 0. Enter, and we have this point. This is going to be the center of mass of our point. As you know, just like for the reference point, the moment we create a datum point, if I now launch a simulation, it doesn't even print it in the input file. We have to do something to tell Abacus. First of all, there put a mass of 300 kilograms more or less, and then connect it to. No, we have to connect it to the reference point we cancelled. Sorry. So let's create quickly again the reference point. But you know how to do it. It's here again. Activate, deactivate, cut. It even saved the one we had before. And then tools, reference point is this one. All good? I don't know why I took this initiative of deleting that thing, but I shouldn't have done. then we also have to apply the coupling. So actually, sorry. Anyway, now it's just to show you the command. Anyway, okay, this we have. What are we going to do now is, yes, first of all, let's attach the mass to the point we just created. See, this is because Abacus doesn't have an undo button, because that would have been very easy to undo. Unfortunately, it doesn't. Anyway, yes, special. This is what we have to use. Here we have some commands to do a lot of things. Actually, I work a lot with special crack, but today we're going to do inertia, special inertia. Yes, sorry, special inertia. Yes, tools. No, yes, yes, special inertia, point mass inertia. No, sorry, wait, guys, I'm making, yes, sorry, first we have to do something else, sorry, I'm losing a bit of, yes, I'm here, yes, tools, attachment, points from file or by picking, of course we're going to do by picking, so point from file by picking, I select with this edit the point we just created, and I click OK. Now, with that with that green plus, I have told Abacus this is something interesting that I'm going to use later to attach something. How to connect that point to the reference point that we created? We have to use something that is very similar to the sections that are the connectors. So first we have to create with this command a wire between the point we just created and reference point 1. If I do this, create wire, this, you want me to repeat some stuff? This opens up, add, from the green X to the reference point 1. Done. Okay, and now if I zoom in, I have this blue dashed line that goes inside the crosshead because it's connecting the 2 points. This is a line, this is now a wire, it's geometrical, purely geometrical, it's still nothing mechanical. For it to be mechanical, we have to do, again, we have to assign to this wire properties. And we do it just like to parts we assign section. First we create the section and then assign it. Now, first we create a connector section with this command here, create connector section, and then we will go into assign. So create connector section, beam. Okay, to call it the connector assignment 1. Be careful here that we have a lot of possibilities. I don't remember what all of them do. If you need, for example, not a rigid beam like we are going to use, but something that, for example, allow a relative torsion, there is the option to do it. You just have to look in the documentation which ones. Anyway, continue. Here we touch nothing, but we also have a lot of options to, don't do it because we're not going to do it. We have, for example, to add the options to add failure. So, for example, yes, it is rigid, but the moment the force, these 2 points are exchanging, exceeds a certain value, the thing collapses, for example. We can even give anisotropic properties or even finite rigidities to these connectors. For now, let's just click OK and everything is going to be rigid. We have created the section, just like the sections. Let's assign the sections using this other command, connector assign. This one, select the wires, is going to be the blue one. Done. The connection we just created. Click OK. And now this is a beam, a rigid beam between the 2 points, as Abaqus kindly reminds us. Let's go back. That point is a notable point. It's not just a point floating into space now, but we still have to attach the mass to this point. Here is where we go with what I was saying before, special inertia create. Of course, it's point mass inertia. Continue. Select points to assign point mass inertia. Of course, is the point that we have. Done. And here I can start selecting, not selecting, inputting all the numbers that I need. For example, mass, let's have a look again. 306 kilograms. So isotropic 306, right? No. Tons. We're working with Abaqus in tons. So 0.306. Inertia. Moments of inertia. Here we make, first of all, what do we have here? Here we have kilograms per meter squared. Kilograms have to be made in tons. Meters have to be made in millimeters. Basically, all these numbers we have to multiply by 1000. Moreover, of course, we have to check that the axes that we are given correspond. For example, axis 1 for us is the x-axis, that's correct. Axis 2, however, for us is z. So here in I22, I have to put what here I have in I33, and vice versa. So let's start to put. In I11 we have 627, 1, 2, 3 zeros. I22, again, I22 is the vertical one. That here is I33, actually IZZ. So 68 times 1000, 68, 1, 2, 3 zeros. And this one is, yes, YY 668. 668, 1, 2, 3 thousand. Okay. Now, what about the off-diagonal terms? In principle, I have to put the off-diagonal terms. The problem, what is that here I don't know the orientation, the initial orientation of the coordinate system on which this was calculated. So what I can do is I can say, okay, you know what? I'm not going to give you the off-diagonal terms, but I'm going to tell you that the coordinate system to be used is not the global one, but is one that is oriented in the same way, but that goes through the point that I'm going to use. And in that way, I don't need to specify the off-diagonal. To do this, I do tools, datum, coordinate system, offset from coordinate system. Rectangular is fine, continue. Select a datum coordinate system from which to offset. We're going to select this one. How do you want to specify the offset? Of course, it's much easier if I select a point, and I select the point that I'm using. And you see that now it created the same coordinate system just translated, and I can do here edit coordinate in the menu of the edit inertia, and I can select the new coordinate system we just created. I click OK, and now in that point we have defined an equivalent mass that represents the spindle. Remember, we have to recreate the coupling, so very quickly. Create constraint, coupling. Sorry, I made you deleted it. RP1. Continue. Reference point 1, we select this. Done. Then I go into the front view. Node region as secondary. And then I do this, and then this, and this. And let me also make sure I don't select the point. Okay, done. The coupling was made just like before. So we have basically the same simulation as before. We just apply the mass of the spindle there. We ask for a quick frequency analysis. Boundary conditions, are they still there? Let's check. Yes, of course, because it was created in the initial step. Loads, is the load still there? No, it exists, but it was suppressed because the its step was suppressed. Are we finished for a dynamic analysis? This is often the trick with when you receive files from other, or you create your own file intended for something and then you have to do something else, especially dynamic analysis. Yes, we defined the steel. We didn't give the density of the steel because we didn't need it. It's not a mistake. It's we don't need it in a structural simulation. We need it in a dynamic one. So we go back to property, material manager, edit. We add general density. The density of this thing is the one of the steel in tons per millimeter, so you can imagine it's a very low number, and it is 7860 to the power of minus 12, E minus 12. And I click OK. Now we are actually ready to launch the new job. So I create a new one and I call this 02 dynamic machine tool. Continue. OK. And I launch the simulation. Let's see what happens. Finished. Yes. Results. So let's start from 0. 0. First eigen mode. I have this mode of vibration at a frequency of 15 Hertz, 15, almost 16 Hertz. Let's also put a bit of engineering sense. Does this make sense? It doesn't make sense that this is the first mode of vibration. But yes, there is a mass that is completely concentrated on one of the side. Of course, this thing is going to start vibrating on that side. So it makes sense that this mode of vibration happens at a lower frequency than the following ones. Next mode of vibration, for example, is this one. And indeed, this one requires the mass to be lifted rather than to be lowered. So this indeed, it requires a higher frequency, higher energy. And then we have these modes of vibration, which looks even independent on the mass that I have there, which makes sense if we are at a very high frequency. And again, these are all the other modes of vibration. Once again, here, for example, I have a displacement, a maximum displacement of 1 point whatever. In the last one, I have, for example, 6 point whatever. Does it mean that I have 6 millimeters there? No, we said it. This is completely meaningless. This is just to give you an idea of the deformed shape. And these are values that are normalized. They do not have physical meaning in the numerical analysis. In the dynamic analysis. And in fact, I cannot even select the stress. Of course, how do I get the stress from a frequency analysis? It's a mode of vibration. And of course, there's no load applied. Clear questions, doubts? Okay, if not, I will see you next time. Next week is the last, let me stop. Next week is the last